Okay, this is the second part of problem 2 from the Thursday, 8 September practice problems. It's the RLC circuit. The first part of the problem, we found the differential equation. We transformed it into the Laplace domain, and we solved for the inductor current in the Laplace domain and got this 3-term expression because we had the input Vs of S and its own coefficient in terms of S. We had the initial condition on the current, IL of 0, and we also had the initial condition on the derivative of the current, IL of 0. So when we need to find the transform of the input, which is 200 volts, that's easy. So Vs of t, for t greater than or equal to 0, Vs of t equals 200 volts. So V sub S of S is 200 over S because the input's constant. So we get transformer constants 1 over S. And now we have our initial conditions we can apply, and luckily one of them is 0, so that's going to make that second term go away. And the other one is 5 amps, so that's going to turn into a 5 there. So let's plug these numbers in. Oh, we need the numbers for the parameters. We have a 1 over RC term to worry about. So let me see, R is 20 and C is 2.5 milli. 20 times 2.5 is 5. Right? So 5 milliseconds is sort of a time constant for RC there. And when we take 1 over that, we get 1/5. Let's see if I did this right. 20 times 2.5 would be 50. 22s is 40, and half of 20 is 10. So that would be 50 times 10 to the minus 3. So 1 over RC, and I know y'all don't like this, but this is old school thinking about how you shove numbers around and figure out what they are without using a calculator. So again, I make this smaller and I get 1/5. That means I make this bigger, which would be times 10 to the minus 2. So 1/5 times 100, and 1/5 of 100 is 20. I know y'all hate that. LC is going to be, you're going to have the same response there. So that's, LC is 0.4 henries times 2.5 microfarads, or millifarads. Let's see if I can do the arithmetic right this time. 4 times 2.5 would be 10, and I think I got a 0.1 there, right? 2/5 of 2.5 is 1. How about that? So 1 over LC is 1,000. So now we can plug those in for our parameters up there. 1 over RLC is going to be 1. Let's see. 1 over RLC is going to be 20 into 1,000, which is 50. So let's see. IL of S, 50 over S squared plus 20S plus 1,000 times V sub S of S, which we've lost down here someplace, 200 over S. And then we've got S plus RC, 1 over RC, 20, again over the same denominator, S squared plus 20S plus 1,000 times 5 milliamps. Hopefully everything's, or not 5 milliamps, 5 amps. This problem's in whole amps because we've got 100 volts and 20 ohms. So it's really 2 different problems, and we're going to work it 2 different ways. We'll do partial fractions on this one because we have the input here, but this is just a something over S squared plus 20S plus 1,000. If you want to, you can take my word for it, but remember from quadratic formula, b squared minus 4a. If b squared minus 4a is negative, then you're going to get complex roots. And indeed, we're going to get complex roots here because 4ac, c is big, and squaring that's not going to make b squared. It's not going to be. It's going to be 4,000. We're going to get complex roots. You'll see in a second. In fact, we can get there by completing the square, right? We could write this as 50 over S plus 10 squared plus 900. So that's S plus 20S plus 100 plus 900 for our 1,000. 200 times 50 would be 1,000, 10,000 in the numerator here. We'll carry this along for a second until we get 5 times S plus 20 over S squared plus 20S plus 1,000. Yes, you have every right to complain about 5s and S's in the same problem. We know the roots of this are going to be, and we lost an S, the input S here. So we have all this times S. So we have our S input, and then we have the roots of this, which are minus 10 plus J30, plus minus J30. So the root in the upper half plane at minus 10 plus J30, and then a root in the lower half plane at minus 10 minus J30. And that, we'll do the partial fractions on that. And then again, we've got this other term over here, 5S plus 20 over S squared plus 20S. Here, let's go ahead and write it in the same form. Okay, these all have the same, this has the same denominator, this has the extra S. Remember, that means we're going to get an e to the minus 10t sines and cosines at a frequency of 30 times t. So we're going to get both terms, both the input term and the term from the initial condition current are going to have those kind of components in them. Let's dive in and do the partial fractions. Painful it is. We only have to do 2. We have the coefficient of 1 over S. We have the coefficient of S with a pole at minus 10 plus J30. And then the other one has to be the complex conjugate of that. So we can take that one. Minus 10 plus J30. Cover up. Let S equals 0. And now we have to find the weight at S equals 0. And let's see. We plug that in. We've got 10 minus J30 times 10 plus J30. That's something times its conjugate. So we get 10 squared plus 30 squared. We've got 10 times 10 to the third over 10 squared plus 30 squared. Oh, that's back to 1,000. So we've got 10,000 over 1,000, and that's 10. And I hope that's right. We'll see. And now the more complicated one is when we cover up the S, the one with the root of minus 10 plus J30. And so we have to let S equal minus 10 plus J30 in all these expressions here, going with the lower. We still got this other term to worry about. We'll get to that in a second. So we've got 10,000 in the numerator. We get minus 10 plus J30. And we get minus 10 plus J30 plus 10 minus J30. Plus 10 plus J30. This works out pretty consistently when you're doing partial fractions with complex pole pairs, is that, I mean, this is for second or third order, not when you get like 10th order stuff. You have lots of terms there. But you notice when you plug in the root at the conjugate term, the real parts cancel out and you're always left with the imaginary part there. Let me do a little side work over here. We've got 10,000 over minus 10 plus J30, and then we've got J60. And there's, as many different ways to do this as there are people. You can pull out a 10, you can pull out, you can make your life easier by pulling out a 10 to start with, 10 out of there. Pull out a 10 out of each of these. And so you're pulling out 100, so you get 100 over minus 1 plus J3 times J6, and that may make things a little easier to work with. So we've got 100, J3 times J6 is minus 18, minus 1 times J6 is minus J6. We could simplify some more there if we were bold, but let's don't push it. Let's do it. Let's push it. That's minus 3, 6 times minus 3 minus J. It just makes getting the conjugate part out of the denominator easier. So we get minus 3 plus J over minus 3 plus J. That's just 1, and that the conjugate of the denominator form. And we've got 100 times minus 3 plus J, and then we've got 6 times 9 plus 1. So 10 goes into 100 10 times, and then I can leave the 6 there and have minus 3 plus J. I could have minus a half plus a 6, J. 10 6 is the same thing as 5/3. So it could be 5 minus 5/3 plus 5/3. Minus 5 plus 5/3 J. You get lots of different ways of writing it. And I'm hoping, again, I haven't been looking at my notes, I'm thinking that's the right thing, but of course I simplified it differently in my notes. Let's see. I'm trying to think if I can do a quick check here. This will be the conjugate term, so this will be minus 3 minus J on this side. This is the one that matters to us. It's the residue of the pole with the positive real part, and the pole is at minus 10 plus J30, so the residue to that here is 5/3 minus times 1 minus 3 plus J. And to get the inverse transform, I'm afraid to erase all that in case it's wrong and y'all want to go back and fix it. 10 is 10. 10 over S is 10. You take twice the real part. So it'd be 10. Minus 10 is the real part. And then you have E to the minus 10t, different 10. And then you have cosine of 30t. And you take negative, twice the negative of the imaginary part of the residue, and the imaginary part is 5/3, so we'd have negative of that is, and twice it is minus 10/3, same decaying exponential, same sign. And when I worked the notes, I had the original printed values of 6 volts and 10 volts and 6 volts over there, so my answer, I can't check it for sure. The process is right. The way I worked it here on the board is a little bit different than what's in my notes, and so there's a chance it's not perfect. There's a chance I've screwed something up, but that's the general process. We got one more term here we haven't dealt with yet. That's this one over here. This is just a proper rational function with a complex conjugate roots, and we can get to the answer by hook or by crook, and we're going to go by hook or by crook to get there instead of doing partial fractions. I'm just going to go ahead and write down here to hide this. I need some space. We had our K was 5/3 minus 3 plus J. So I can erase this stuff here. That's how we got back to this 10 for the minus 5 was the real part there. That gave us the minus 10. 5/3 was the imaginary part. That gave us the minus 10/3 there. But I want to take a minute to work with this other term here before finishing this up. We know that cosine, if this were e to the minus 10t cosine 30j, we would have s plus 10 here. We know if it were sine here, we would have 30 over this stuff down here. So what we want to do here is shove symbols around until we get that. So we take the 5, which is going to be an amplitude, and we write the s plus 10 part, s plus 20 part as s plus 10, and have s plus 10 squared. The denominator stays the same. So there's our 5, s plus 10, and now we've got our sine term, and we took 10 out of this 20, so we've got 10 left. So we've got 10 over s plus 10 quantity squared plus 30 squared, but we want that to be a 30. So, okay, we divide by 3, we multiply by 3, so now we've got a 30, and so we can say that the first term from this part of the expression is 5 e to the minus 10t cos 30t. And the sine term from the second part of the expression is plus 5/3 e to the minus 10t sine 30t. And then you can combine the weights here. If you want to combine the 5 there, we get a minus 5 and the minus 10/3 and the plus 5/3, so we get a minus 5/3 to get the total answer. So it's a bear. Anytime you have the complex roots, it's a bear. And that's why MATLAB does that for you. But you need to also have a sense of how to work them by hand. I mean, the key points are, once you get to this point, you say, oh, this is going to be e to the minus 10t cosine 30 plus something e to the minus 10t sine 30, and then you've got your constant term here from the s there. And you're going to have the same stuff happening here. And again, when you've got this s plus something over your quadratic denominator with complex roots, you can shove stuff around to make it fit the form you want it to have. S plus alpha over s plus alpha squared plus beta squared, beta over s plus alpha squared over beta squared, and do the inverse transform that way.